All right. Assalamu alaikum, guys. Hope all of you are doing well. So, in this series of live past paper sessions, you guys obviously know that's because you've signed up. That's how you know. So, you know that we are going to be looking at some of the topical past papers. Sorry, some of the yearly past papers. And it's going to look at all of 2023, including IGCSE, including O levels. And it's going to look at both of the P2s and P4s. So if I'm correct, then you have your P2 on 13th May, and then you have your P4 on 16th May. So not a lot of time between the two. So we'll just be prepping for both of these in these sessions that are to come. So yeah. So today, as the agenda was already shared with you, we are looking at the summer 23, paper 21. So let me also see that you guys have access to chat, because that's where you'll ask questions. Just try not to spam a lot, just becomes really distracting. But let me just enable that you guys do have access to it. So, all right. So check that you guys can use chat. For some reason, can't seem to do it. All right. So I think your chat options are with me directly, or can you also chat with the entire group? Like, I know I can message everybody. So you guys can only message me and the post. All right, that also works. I guess that's a good way to avoid spam. All right. Yeah, so we're starting with summer 23, paper 21. So let's get into it. Also, just something about how we are going to take the preparation of these papers forward. So you know that in your P2s, you have a time of 1 hour and 45 minutes. This is the theory paper that we're talking about. And for each theory paper, you also have a mark of 80 minutes. To be extra strict on yourselves and to just really get into the habit of solving a lot of papers and doing it in a good time, the mental limit that you should have on yourselves, what we'll also be imposing on ourselves in these sessions, is that the number of marks is also the number of minutes I'm going to be giving myself. So right now it's almost 6:10, which actually leaves us with exactly 80 minutes. And that 80 minutes is what I'll be aiming to do this paper in. This is also what you should keep in mind, that whenever you are doing papers on your own, this is the time limit that you should have. So 80 minutes is like 1 hour, 20 minutes. If you manage to do it at home in this time, then inshallah, when you'll be sitting for your papers, you obviously will be able to get done in this time, right? So yeah. So now let's get started with the paper. So this is June 23, paper 21. Let's kick this off. So June 23, paper 21 is the first paper of the series of live sessions. First off, we are starting with this one. An aircraft pulls a glider along a runway as shown in 1.1. So there is the actual aircraft, which also has an engine, as all aircrafts do. And connected to this is a glider. So the glider does not have any engine, right? This is one key aspect of this question, which is going to be discussed later. So 1.2 shows the speed of the glider during the first 12 seconds of the motion. Now, whenever faced with a kinematics graph, this is the steps you should take, because this is the most foolproof method of doing all kinematics graphs. First off, you must always observe what the axes of these graphs are. So this in particular is a speed time graph. Now, when you have identified what the graph is, so in your syllabus, you know it could only be a distance time or a speed time graph. Now that you've identified that this is actually a speed time graph, then you need to write down its features. What I mean by features is what is the area, what is the gradient of this graph, generally speaking. I don't want you to calculate it just right now. So you know that the area of this graph is the distance. And similarly, you also know that the gradient here is acceleration, right? Now you know this stuff. The first part of the question says, describe the motion of the glider in the first 12 seconds. So I can see that from here to here, from 0 to 6 seconds, the speed is increasing. And to put it more precisely, I would say the speed is increasing uniformly, right? Because it's increasing in a straight line. And then whatever speed it does hit till this point, it has the same speed throughout. This is how I'm going to answer this question. So I'll say this, that from 0 to 6 seconds, the glider accelerates uniformly. And in doing so, it reaches a speed. Now let's try to see what this speed is. So let's have a look at this axis. So the scale basically. So 20 to 25, and there's also a difference of 5 small boxes in between. So this is very easy to see. This must be 21 and this must be 22. So it reaches a speed of 22 meters per second. Then I'll say that from that 6 to 12 seconds, it travels with the constant speed of 22 meters per second. Very straightforward. All right. Part A done. Very easy, very straightforward. Part B. In the first 6 seconds of the motion, there is a resultant force of 1800 Newton on the glider. Whenever in O levels I see this word resultant force, automatically my mind is going to be triggered to think of Newton's second law. Right? This is what resultant force relates to. So it's the resultant force which we are talking about here. In the first 6 seconds of the motion, there is a resultant force of 1800 Newton on the glider. Also in your syllabus, the form of Newton's second law is this: resultant force equals mass times acceleration. It then says, using the increase in the speed in the first 6 seconds, calculate the mass of the glider. So I am given the F, I want M, and using the graph, as is also very explicitly stated, I can find out the acceleration. So remember, the formula for uniform acceleration is this: V minus U over T. Let's make this a bit clearer. So V minus U over T, where V is the final velocity, U is the initial velocity, and T is the time. So here the final velocity, if you remember, then that was this, which it reaches at the end of 6 seconds, which was 22. It started out from 0, so that's its initial velocity, and it does all of this in a time of 6 seconds. So when I'm going to calculate this, then this is going to be 22 minus 0 over 6, right? So this is going to be what? 11 over 3, so 3.67 meters per second square. And then in the next part, because you need M, you know, this is going to be F over A. So 1800 over the answer from the previous part. Again, to avoid rounding errors, you should use whatever the calculator answer gives you. So you should do 1800 over the last value stored in your answer variable in your calculator, which is going to be this thing. That just avoids rounding error. So what answer do we get here? I can also get my calculator. So 1800. So 22/6 was 3.67, and 1800 divided by this is 490.9. So 490.9 correct to 2SF. If you want to give this would be 490. Or if you want to do it to 3SF, it's going to be 491. All right. Now, just a sec. Let's, yeah. Okay. So this part is pretty straightforward again. Let me know if you have questions in the chat. Part C, determine the distance traveled by the glider in the first 6 seconds of its motion. Now, in doing this part that we just did, part B, we use the idea that the gradient of a speed time graph is acceleration. So we used this feature here. Now, since we need the area, since we need the distance, we'll use the area, right? So we need to find the area of the area under the graph for this first 6 seconds, because that's the distance that we need. So this is very straightforward. This is just a triangle. In this triangle, we know that this base is 6, and we just also worked with this height, which is 22. So we just need to use the area of a triangle. So half base into height. So area is half base into height. So half into 6 into 22, which is going to be 66 meters. All right. Next part. Part D. The glider has no engine and stays in the air with the use of convection currents. So now all of a sudden in this question that was supposed to be kinematics and forces, we now also have to do a part on heat. State what is meant by a convection current. Do make a mental and also write this down, make a written as well as a mental note of this, that whenever you are asked to explain convection ever in any question, you have to use the word or the term of density somewhere. All right. So D part 1, state what is meant by a convection current. So you know that the rising of hot air, in this case it's going to be air, otherwise I would also say water. So the rising of hot air because it's less dense, and then the falling of colder air because it's more dense. And that movement that it constitutes is what is known as a convection current. So I'll say falling of colder, denser air and the rising of hotter, less dense air. Right? This is what this is what creates a convection current. Now, part 2 is one of these parts that I warned you guys against previously as well, which are the suggest parts, the most difficult parts in all of O-level physics. Now, why are these so difficult is because you just can't prepare for it. With the suggest parts, the examiner assesses your ability to think on your feet. Now, it says that the glider has no engine of itself, as I also told you in the start, and this stays in the air with the use of convection currents. Now, it's told that it stays in the air with the help of convection currents. Now you are asked to suggest how does this convection current, which supports the glider, how is this formed? So there could be a lot of ways in which you can talk about this. Also, this question is slightly weird, so the examiner was also willing to give out marks for a variety of responses. First off, if we go back to the diagram again, so we can see that the glider is pulled along by the aircraft, right? And right now, we don't even know if it's taking off or if it's not taking off, what's happening. It's not very clear. Then it says it does stay in the air with the use of convection currents. Now for convection current, you know that there must be some rising of the hot, less dense air, and it could be the falling of some cold, denser air. So now you have to think about how could that convection current be developed. In my mind, the first thing that I think about when I think about the convection current in this case is the idea of the land breeze and the sea breeze, which is that when the hot air above the land would rise, it would create a convection current because the colder air would then fall, right? So I can say this, that some hot land causes air above it to rise since it's less dense. And the colder, denser air would fall. Whenever faced with suggest parts, you obviously know that there is going to be some element of doubt here, because you don't know for sure until the mark schemes come out that what exactly the examiner was willing to award marks for. So write as much detail as you can for these suggest parts. If you write a lot of stuff and if the examiner finds out that there is something of substance that you did write down, you will get the mark for that, even if the other stuff is not completely relevant. So that ends question number 1. Any questions so far till this point? I guess the last part was the only one which was slightly tricky. All right. So the next one. In a safety test, a car of mass 1100 kg travels at a speed of 10 meters per second and collides with a stationary van of mass 3000 kg. After the collision, the car and the van move together with a velocity v. Moving together, sticking together, moving off together, these all hint towards a very specific case of the conservation of momentum cases, if you remember. When they move off together, it basically means they stick together. And when they stick together, you know that when I'll write down the expression for the conservation of momentum, since they both are really now one object, I'll add their masses, right? This is the cue that the examiner is giving you by saying these words. Then it just shows the diagram which shows all of this data before and after the collision. Total momentum of the car and van is conserved during the collision. You know this. This law is known as the conservation of momentum. In A part 1, it says define momentum. It's very straightforward. So just mass times velocity, or you can also write it like this, product of mass and velocity. State the unit of momentum. So units of momentum are 2. You can write any one. The first one that you get by multiplying mass and velocity is kg meters per second. And the next one that you get from this expression for impulse, basically, delta P is F delta T. So the other one you could write is Newton second, right? Not Newton per second, it's Newton second, right? So you could have written either this one or this one, any one. Part B, calculate the velocity of the car and the van after the collision. So we'll use this idea that total momentum before should equal total momentum afterwards. Now, remember that when I taught you this, I always told you guys to write down this thing first, which is that total momentum before equals total momentum after. So if we think about the total momentum before, that's just the momentum of the car, really, because the van has no velocity, right? So you can also say that it's just 1100 times 10, but if you're really insistent on writing this term, you would say it's 3000 times 0, which is a 0. So 1100 times 10 is the total momentum before, and the total momentum after would be whatever this velocity is times this mass. So this is now going to be the combined mass, the 1100 of the car plus the 3000 of the van, which makes it 4100. All right. So this question was relatively easy because we didn't even have to use the sign convention. It was moving before the collision in directions towards the right, and afterwards it's also moving towards the right. So this was very, very straightforward. So now I just need to calculate this 11,000 over 4100. So this turns out to be 2.6829, 2.68 or 2.7 meters per second, correct to SF. Yeah, you will receive the recording for the class. All right. Calculate the total kinetic energy of the car and the van after the collision. So now we know the mass afterwards, we know the speed afterwards. So we can just use the formula half mv squared, right? So it's half. Mass is 4100 as we calculated. And the speed is whatever your answer was. So 2.6829. I'm just writing this down here so that you know that you have to take more significant figures here. All right. Otherwise, obviously, you're going to use the values which are there in your calculators. So the square of my answer times 4100 divided by 2 is 14,756, or I can say this is 15,000 joules. All right, you can also write your answers in standard form if that's what you like. So state the transfer of energy that occurs in the collision. So in this collision, what's the transfer of energy? Because if you do this calculation, you don't have to, by the way. You'll find out that the initial kinetic energy is more, the final kinetic energy is less. So where is that energy going? So you'll say that the kinetic energy of, which is basically due to the movement, the kinetic energy is transferred to heat, so to thermal energy, and would also be transferred to sound energy. All right. So this is how the energy is transferred. Question number 3, a circuit containing 3 resistors, a 12-volt power supply, and an ammeter is shown. Calculate the current in the 400 ohms resistor. Now you can see that this voltage source is in series with all of these resistors, the 400, the 200, and the 100. So the current through the entire circuit is going to be the current through the 400 ohm resistor as well. So first off, let's just calculate the total series resistance, which I know is just going to be the sum of all of these, which is 700 ohms. And then I'll just use V equals IR. So I would be V over RT. So V is 12, RT is 700. So if you just find this out, 0.0171 amperes, correct to 3SF, right? You could also give it just to 2 by saying it's 0.017. Calculate the power produced in the 400 ohms resistor. Now, for some reason, power is a bit confusing, electrical power, because people don't know what formula to use. Well, it's very straightforward. You can use any one of these. You can use P equals VI or I square R or V square over R, but make your life easy. try to use something that you already have at hand. For example, I know the resistance of this resistor and I also know the current. I do not know the voltage. So let's not first try to find the voltage first. Because I have a formula which works solely with current and resistance, let's just use this. All right. So I square R. So 0.01714. Again, this is just to show that you should use your calculator value times 400. So the square of this times 400 is 0.11755. So 0.118 watts. I guess you guys, when you will be doing this paper on your own, the homework paper, you'll also see that in this 2023 paper, there's a sort of a different trend that a lot of units are already given for you. I also just noticed this. Units are already given. Otherwise, in the older papers, remember that the unit you would mostly have to write on your own. Part C, a student uses all of the components shown in 3.1 in another circuit. She connects them so there is the largest possible current in each resistor. How could each resistor have the largest possible current? First off, you need to think about such a case. Now I know that resistance is V over I, right? Or if I rearrange this, I can also say V equals to I R. I know that the resistance of each resistor I cannot change. So this means that if I do actually want each current to be the largest, it should also have the largest voltage across it, the largest possible voltage. Now, you know that as we were looking at this circuit above, in series circuits, the voltages split, right? And when the voltages are split, this will also cause the resistance. This will also cause the current through each resistor to be the smallest, right? Because here the total resistance was the largest. If you want the largest possible current, then you need the entire EMF of the supply across each resistor. You know that the name for this certain configuration is parallel. All right. The current in one of the resistors is larger than the current in the other two resistors. The student connects the ammeter into the circuit to measure the current in this resistor. Draw the circuit diagram of this arrangement. Label each resistor with the value of its resistance. Right? All right, so let's think about this again. So largest possible current in each resistor. So in each resistor, we need the largest current. So we said that we are going to connect this in parallel. The question then says the current in one of the resistors is larger than the current in the other two resistors. All right. So if the current in one of the resistors is larger than the current in the other two resistors, this means that we are now talking about the smallest resistor. Because what is resistance really? It's the obstruction to the flow of current. It's the hindrance, it's the stoppage. For the current to be largest, this means that we are going to put the ammeter into across, we are going to put the ammeter with the resistor, which has the smallest resistance. That's going to give us the largest current, right? So when I now make this is going to be 12 volts. So the 12 volts. But now it's going to be in series with everything. It's going to be in parallel with everything. So this is your 400 ohms. This is going to be your 200 ohms. And this one is the one that you want to measure the current through. Remember that ammeters are connected in series. And this is your 100 ohms resistor. Just sure, mine, just shoot your questions. I'll just look at them through chat. Because that's what happens in parallel, right? If they want the current to be larger, this means that, all right, look here. Think of it this way. If we were previously doing this, just close this thing. So yeah, previously what was happening that the current was flowing through all of this. And when the current flows through all of them, it has to go through this resistance and this resistance and this resistance. So it faces the combined resistance of 700 ohms. But when I connect it in parallel, then the same voltage now appears across much smaller resistors. It appears across the 400, across the 200, and across the 100, right? So now it faces smaller resistances. The resistance of this parallel combination, you must know that the resistances in parallel are much smaller than the resistance. Oh no, just a sec. So the resistances in parallel are smaller than the resistors in series, if you're talking about the same resistors. Let's just get this going again. Does that make sense? All right, should we go on now? Okay, all right. Let's play this again. So we're done with 3 questions in 25 minutes, not too bad. A student pushes a drawing pin into a wooden board as shown in 4.1. The area of the pin in contact with the finger is this much. The student pushes downwards with a force of 26 Newton. The mass of the drawing pin is very small, so this means that we are supposed to ignore this. Calculate the pressure exerted by the finger on the drawing pin. Very straightforward. We know the formula for pressure is force over area, right? So the force here was given as 26. The area is 5.0 times 10 to the negative 5. So we just plug all of this into our calculators. So 26 over 5 into 10 to the negative 5 is 520,000, or in standard form, 5.2 into 10 to the 5 pascals. Now, part 2 is also really important because it does lead up to part 3. It says compare the force exerted by the finger on the drawing pin with the force exerted by the drawing pin on the wooden board. So as you can see here, this guy, whoever is pushing down here, is applying a force here. How does that force compare with this force that the nail, the pin now applies on the board? The answer to this is that the forces are the same. The push that I apply on the top is transmitted all the way down through the wooden board, right? What force I apply at the top is what force goes down as well. If I just make a diagram to further explain, if somebody is confused here, which is that you know that if I'm talking about, for example, Newton's second laws, you know that it doesn't make a difference if I mark a force F here or here, right? It's the same thing, because the force which is applied here is also going to be transmitted further down the road. All right. Now, part 3 is to be answered keeping this in mind. Explain why the drawing pin goes into the wooden board but not into the finger. Now we have to explain this. Why does the pin go into the board but not into the finger? For this, you must focus on the design of the pin itself. This has a large area, whereas this one has a really small area. So you know the same force is applied, but where the area is more, the pressure is going to be smaller. Basic inverse proportion. The value of a fraction is always inversely proportional to its denominator. So if the area is larger, the pressure would be smaller, and vice versa. Here, since the area is smaller, the pressure is larger. This is exactly what I'll say here. At the thumb, the area of contact is larger, leading to a lower pressure. You could have also written this statement by the perspective of the lower end of the pen. So just to make this very comprehensive, I'll also say similarly, or rather, it's not really similar, it's rather in contrast. In contrast, the area at the pen, area at the board is smaller, leading to a larger pressure. Either one, by the way, was correct here. It was sufficient. But just to make sure that I cover all the points, I've written this from both point of views. All right, part B. 4.2 shows water emerging from a plastic bag that contains a number of small holes. The first part explained why the water emerges from each hole in a direction at right angles to the surface of the bag. Now, this is something which was new in your syllabus at the time of this paper. I mean, it's still a new addition as compared to the older syllabi, but at this time, it was something which had never been assessed before. Whenever something is new, which is added to the syllabus, it will definitely be assessed. And hence it was in this paper. So it says, why does the water emerge at a direction which is at right angles to the surface of the bag? For this, you need to know a property regarding liquid pressure, which is that the pressure of the water in the bag this creates a force, but that force is very specific in direction. So this force is at right angles to the walls. And in this case, because it's not really like a box or something, then rather than walls, I should say, to the surface of the bag. Now, what this means is that if I have to show you this on this diagram here, then the water inside the bag is going to exert a force which is going to be at right angles to the inside of the bag, basically. So right at this point, when the water emerges, it goes out at right angles, right? I have to do this. Right at the point of contact, it's at right angles. So it emerges at 90 degrees. And the reason is this. The pressure of the water exerts a force which is at right angles to the surface of the bag. All right. Sometimes the examiner might also reverse the question here. They might ask you to define a experiment in which this is shown that the pressure of the water in the bag exerts a force which is at right angles to the walls of the container. In that, you'll just describe this experiment, that when you make holes in such a container or in such a bag, the stream of water which comes out is at right angles to the surface. So when it exits, obviously, it will curve downwards, but right at the point when it exits, it's going to be at 90 degrees to the container, right? All right. Holes at A and B are the same size. Explain why the water emerges faster from the hole at A than from the hole at B. Now, this is pretty straightforward. This is also something which has been asked a lot in older papers. So you can see that A is at a greater depth below the surface, and this is not at as much of a depth. So since the depth is less, the pressure here would also be less, right? If I just write down the formula for it, you know that pressure is given by rho g h. H is the depth. So I can see that pressure is basically going to be proportional to the depth. So I'll say why it emerges faster from A is because A is at a greater depth. And the liquid pressure is greater here. All right, so I see we have a question. Say I equals to T. What's I equals to T? So it should always be at right angles. The force that a liquid applies, the force that is due to the liquid pressure in an object, yes, it's always at right angles, right? Even you can also show this in a diagram like this, where you have all of these holes, for example. Let's say this is the liquid level. So if I make a hole here or here or here, I know that from the bottommost point, because the depth is the largest, it's going to go off at the greatest distance. Then this one is not going to go off as much. This one will go off the least. But if I look at either of these, it's at right angles to the surface. This is the idea. All right. This makes a 90-degree angle. So we're also done with. All right. So we're also done with this. Let's go on to 5. Explain using ideas about particles why liquids expand more than solids for the same temperature rise. All right. So what is expansion really? This shows that if temperature increases, the volume would also increase. Now you just need to explain why liquids would expand more. This is something which is explicitly part of your syllabus. So the answer to this is that liquids have weaker intermolecular forces. Forces of attraction. And how does this affect the expansion? Is because temperature in the language of the kinetic model of matter is the average kinetic energy of the particles. So now when the temperature goes up, the kinetic energy also goes up. But because the intermolecular forces are weaker, they can spread out more easily. So their volume increases more, so they expand more. So when temperature increases, particles spread out more. And occupy more space. All right. These reasonings, make sure you have your head wrapped around these. So how temperature and volume correlate, how pressure and volume relate. You should know this stuff. The boiling point of water is 100 degrees Celsius. State the boiling point of water on the Kelvin scale of temperature. You know that the way you convert temperatures in Kelvin to temperatures in Celsius is by adding 273, right? So 100 plus 273, the answer is 373 Kelvin. Part 2, not really a difficult one. the temperature remains constant as the water turns from liquid to gas at the boiling point. This is stuff that you know, that whenever states change, the temperature stays constant. So then you must have also studied this when you were going through this chapter, is that the temperature is not increasing. So that heat energy which is consistently being supplied, where is that going? You can say it in either of two ways. Either you can say it's used to overcome intermolecular forces of attraction, or the other way to say this is that you know that since temperature is not increasing, nothing is happening to the kinetic energy. So that energy which is provided is used to increase the spacing of the particles. So it increases the potential energy. All right. Kinetic energy, remember it in terms of temperature. Temperature goes up, kinetic energy goes up. Potential energy, remember this in terms of spacing. Spacing goes up, potential energy goes up. This is why when something turns from a liquid to a gas, its potential energy increases, and hence its internal energy also increases. Because the internal energy is the sum of the potential and the kinetic energies. All right. Part C. An electric heater is used to heat a sample of metal as shown in 5.2. There is no thermal energy transferred from the metal to the surroundings. So there's no heat loss here. The metal has a mass of 200 grams and is initially at 15 degrees Celsius. The heater switched on for 2 minutes and then switched off. Max temperature recorded is 40 degrees Celsius. Power of the heater is given. Calculate the specific heat capacity. Show your working. Now, first off, when we talk about the specific heat capacity, you must know this formula, E equals to mc delta theta. So you can see that we have mass. C is what we need to find. Delta theta is just 40 minus 15, right? The change in temperature. But E is something we need to find. We don't have that given as readily. Instead, what we do have is the power, and we also have the time for which the heater is switched on. So I also know that since power is energy over time, energy is power times time. Okay. So for energy, power is 20 watts. But remember that the time right now is not in SI units. The SI unit of time is seconds. So it's on me to convert it. So 2 minutes and each minute is 60 seconds. M is 200 grams. Again, now you might be thinking that grams is not an SI unit either. But if you look here, the answer also includes grams. So I do not need to do anything here. I'll keep the grams as it is. If this answer said kg, I would convert this to kg very happily. Because if this is grams and the answer wants me to keep this in grams, that's what I'll do. So 200 C and delta theta would be the change in temperature. So 40 minus 15. If you've written this down, remember that it's a physics paper, it's not a math paper. You really don't need to show any more working. As I do, I'll just plug this all in my calculator and I'll also show you how I do it. It's just entering all these fractions. So I can see that to make C the subject, I would shift this here. Again, don't be risky. If you feel like you just can't do it without writing it out, then do write it out. But I'm saying that it's not mandatory to do that. So I'll do 20 times 2 times 60 over 200 times 40 minus 15 is 25. So just plug all of this in as it is. So this gives me 0.48 joules per gram per degree Celsius. All right. So that's this question as well. All right, next question is related to waves and light. The VR headset in 6.1 contains a display and a lens as shown in 6.2. display is shown, the headset is shown, and the lens and the eye, these are shown. So first off, look at this here, that the lens and the eye are, so the eye is here, the display is here, and this is how the image would be formed into the eye. So the display is the object for the lens. This is the object you're looking at. The lens acts as a magnifying glass and forms a virtual image of the display. So this image is not real. Remember that in all the cases related to lenses we did, there's only one case in which a virtual image is formed. And that is also the case in which it acts as a magnifying glass. This is exactly what is now asked in A1. Describe where the display must be positioned relative to the focal length of the lens for the lens to act as a magnifying glass. That is when the lens is positioned, sorry, the display is positioned at such a way that if I just make a diagram just to show this, that if this is the center of the lens O, then the focus must be here, right? So it must be within the focal length. So it is positioned within the focal length of the lens. If it's positioned at the focal length or any place further out, then a real image would be formed, which is not what we want here. All right, let's just wait for Azan for a while. All right, I think we can start now. Part 2, explain how a virtual image is formed. Now, this might seem like a question which is not really something maybe you've studied explicitly. How is a virtual image formed? So you know that if I talk about this in terms of light or lenses, then you might see that where the dotted rays intersect is where I say the virtual image is formed, right? That's what I say. But remember that what is a virtual image really? Because if we talk about a real image, then the position at where the image is formed, the rays are actually coming out of that point. Whereas for a virtual image, the rays just appear to be coming from that point. It's not actually coming from that point. It just appears as such. So the rays from the image appear to be coming from a point. Right, so where the image is formed. So for example, if the eye sees it here, the image would actually seem to be like someplace here. So it just appears that the rays come from the image. Right? It's kind of redundant here. Let's see if we can make this a bit better. So let's write like this, that the rays appear to be coming from the image. All right. Now, this part, for some reason, students are really terrorized by these lens diagram questions. It's not really all that difficult. An arrow on the display is 3.4 centimeters from the lens. So this is what it means. This is the lens, which is marked L. And the virtual image of the arrow is 22 centimeters from the lens. Oh, sorry. So this is 3.4. So this is 3.4 cm from the lens, and the virtual image is 22 cm, right? O is the object, I is the image. Now this is drawn on the grid with a scale of 1:2. So it's a scaled diagram. Do keep this in mind. It also says this here, that 1 cm represents 2 cm. On 6.3, draw a ray diagram to show the formation of the virtual image I. All right. Now, remember that you have a couple of rules to work with when making these lens diagrams. I always work with 2. So out of those 3, you can choose to work with any 2. So first one, this ray that I'm going to make is obviously going to be like this. All right. What's the idea behind this one is, first off, let's just actually, let's make it this way. Trash this. So you know that if a ray from the object goes through the optical center, it shows no deviation. It remains undeviated, right? And now, because I know the image formed all the way here, I'm just going to take this ray back. Let me do this now. Yeah. Let me see if I can. Yeah. So yeah, approximately this seems right. Then I can use another rule, which is that when an image is when there's a ray which is parallel to the principal axis, when it bends, it passes through uh, the focal length, the principal focus, sorry. But here, if I remember, then the focal length is not given to us. We actually have to find this out. So how would we find this out? So first we've done this one. And then similarly, you know that if I make it like this, and first I'm just drawing this roughly, that if it's going to be like this, it's from the tip, so it's going to go out. But again, when I join this back here, it's going to appear to come from the tip, right? So when I draw this now, what's up with this? Yeah. So now let's make this the other one. It's going to be like this. But now again, I don't know exactly what point it will pass through. But I know that since this is the tip, the image formed will also be the tip. So all that I now have to do is take it from here and then take it like this. All right. This is how this complete image is formed. As you can see, also, this is something I should have done. Obviously, I can't do this on my iPad. Is to show that since this is a virtual image, remember that these rays are not real, right? These rays are not real. In your paper, when you're doing this, to show that the images are to show that the rays and hence the image formed from it is virtual, make these dotted. But I can't do this. Right? So make these dotted. The stuff that I'm hovering over, make all of this stuff dotted. Because these are not real rays. So this is how we get the diagram for this. Similarly, right? These parts are the virtual parts. So they must be dotted. Does this make sense? Because in my opinion, this was a slightly difficult question. For lenses, I've never seen a question like this. It is slightly, you have to really think about this, like how the steps would be. You know what the steps would be, but what would be the order? So draw a ray diagram to show the formation of the virtual image I. This is done. Determine the focal length. Now I'm just raising this arrow for a second so I can see this point here. So if I look at this, this is 1 and so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and another one, right? So this is what? 4 cm, and then this is 4.2. All right. So this appears to me like 4.2 cm. So that's what I'm going to say this is. Again, it might be possible that the actual answer is not this, because as you can also see here, my rays are not really meeting all that nicely here. But when you do it on a paper with a sharp pencil, you might be getting the correct answer. So no problem still here. Should we just continue to blaze through? All right. A water wave in a ripple tank diffracts as it passes through the gap in a barrier. 7.1 shows a diagram made by a student of the crests in the pattern. So crests or wavelengths or peaks, it's the same thing. State one way in which the student's drawing of the crests is wrong. So how is this wrong? First off, you know that wavelength does have an impact on diffraction, but diffraction does not have an impact on wavelength. All right. What I mean to say is that the wavelength before and after diffraction should be the same. This is one of the more obvious ones. So wavelength should not change after diffraction. Another one, which is actually a test of how well you people know the ideas of diffraction, is that never with diffraction will you have a shape like this. With a shape like this, you must remember that your shape is not going to be straight in this middle region. It should be something of this sort. Yes, there's going to be some curvature, and with a gap size this big, the curvature is not going to be as much, but it's still going to be some curvature. Now you know that in a case where there's going to be a lot of diffraction, the crest might look like this. Here, there will still be some curvature, so it would look like this. It wouldn't be exactly straight in the middle. All right. Part B. The gap in the barrier is now made smaller than the wavelength. So now the gap is even smaller than the wavelength. And now you have to make at least 3 crests to show the new diffraction pattern. So now you can see that the wavelength and the gap size are basically more comparable. Back then, there was a lot of difference between them. If I just scroll up, this is the wavelength, this is the gap size. Now the wavelength and the gap size are much closer to one another in terms of values. So when I now make the new crests, it's going to be much more curved. If you feel that for some reason, if you're just clumsy at drawing, if you feel like maybe your diagram has showed that the wavelength has changed, explicitly labeled this that the wavelength before and after is same. Right? It's okay if somebody doesn't have excellent drawing. That's not the purpose of the assessment. If you feel like your drawing is lacking, just write it out. All right. Part C, in one part of the ripple tank, the water wave has a speed of 6 centimeters per second and a wavelength of 2 centimeters. The wave then passes into a shallower region of the tank. Speed of the wave in the shallower region is 4 centimeters per second. The first part, define the term wavelength. How do you define wavelength? There are a lot of ways to define wavelength. The easiest one is this, that this is the distance between two consecutive crests of a wave. You can also see you can also say it's a distance between two consecutive peaks, the same thing, right? Part 2, calculate the frequency of the wave. So for this one part of the ripple tank, we know the speed, we know V, we know lambda, right? So we can find out F, V equals to F lambda. So F would be V over lambda. So it's 6 centimeters per second divided by 2 centimeters. So the frequency would be 3 hertz. All right. Next one. Part 3, calculate the wavelength of the wave in the shallow part of the tank. Now remember that even though this question does not explicitly ask you to use this understanding that I'm now going to discuss, remember this very simple way of determining what will happen to a wave. Remember this, SH shallow, SH shorter. In shallow water, the wavelength gets shorter. This is what's supposed to happen. And we'll also see this happening right now with the calculations. Remember that even if a wave goes from deeper to shallow or shallow to deeper, the frequency does not change. Because the frequency of the wave comes from what is actually generating the wave, right? So in that case, it could be the dipper, which is bouncing up and down in the water, and that's what is creating waves. Here, the frequency will not change. So now I need to find the new lambda. So you can see that if I make lambda the subject, this is going to be V over F. And I know the new V, right? The new V is this. F is 3. So this is just 4 over 3. Never ever leave your answer in O level or in A level physics as a fraction. Always write this down as a decimal, even if it is exact, as in this case. So 1.33 or 1.3 centimeters. All right. Question number 8. A filament lamp is arranged above a shiny metal surface as shown. A student reads in a textbook that a light emitting diode is more efficient than a filament lamp. State what is meant by efficiency. So this is pretty easy. Ratio of useful, saying this is important. Now you can either give this with respect to power or with respect to energy. So you can say it's the ratio of the useful energy output to the total energy input. All right. Suggests why the efficiency of a filament lamp is very low. This might be because if it's wasting a lot of its energy, which is given to it. And you know this, you should know this, by the way, this is just general knowledge, that the filament lamp wastes a lot of input energy as thermal energy. All right. Part B, the student considers replacing the filament lamp in 8.1 with an LED of the same brightness. Data about the filament lamp and a suitable LED are shown here. So input for both of these and the efficiencies. LED emits the same amount of visible light as the filament lamp. So both of these emit the same amount of visible light. What does this imply? This implies that the output is the same. In this case, because power is given, I'll say that the output power is the same for both of these. All right. So the output power is the same. So using the rho for the filament lamp here, I can figure out its output because efficiency is just output over input, right? So 6.2%, if I write this as a fraction at 0.062, is output, P out over input 120, right? From here, I'll get the power output as 120 times 0.062 is 7.44. So the LED gives the same output, but with this input. So I just now use this value again, 7.44 over 15. And because the answer says to give this as a percentage, I'll be multiplying by 100. So 49.6% is what we get. Part C. The filament lamp is connected to the live and neutral wires in the mains supply. Earth wire in the main supply is connected to the shiny metal surface as shown, as it should be. There is a fuse in the live wire. By accident, the live wire touches the shiny metal surface. Right? So now the surface becomes live. Describe what then happens. So now if the live wire touches the shiny metal surface, we know that the metal surface would also become live. But because we do have the earth wire connected to the shiny metal surface, the earth wire is going to carry all that current into earth or into the ground, right? So current flows to the earth. But since there is now going to be a lot of current flowing because of the live wire touching the shiny metal surface, the fuse in the live wire will blow, right? So the fuse blows, breaking the circuit. All right. Part 2, in another similar lamp, the fuse is wrongly connected into the earth wire. Explain why a person is not protected when the live wire touches the shiny metal surface. So if the fuse is connected into the earth wire, what's the problem with this? Because the idea is that if it's connected into the earth wire, the live and the earth wire, there's also still going to be a large current flowing through the fuse. The fuse will still blow. But since the live part is still touching the surface, since the surface is still live, it can cause a shock to whoever touches. All right. In the previous Q, wouldn't the speed change? All right, so I guess we are pretty far ahead now. Let's see if we have time to come back to that later. No, so yes, I think you're talking about the waves question. So yes, the speed did change, right? It was given to us. It was 6 centimeters per second in the first region, and then it became 4 centimeters per second in the second shallower region, right? So the speeds were different. All right. Explain why there is a voltage induced in the coil when the coil is turned. By the way, this is a really good question. because it assesses your learning outcomes. Not this part, this one is very easy, but the later parts. So why is the voltage induced when the coil is turned? First off, you will say that there is a magnetic flux. So for any mention of magnetic flux, you get a mark. And then if you say that the sides of the coil, now you can say two things. So either the sides of coil cut the field lines, or you can say these create a rate of change, or let's say create a change in the magnetic flux, which by Faraday's law induces an EMF. All right. Next one. 9.1. In 9.1, the coil is horizontal with AB on the left. Output voltage is +6. On 9.2, draw a line from each of the shaded boxes to one of the circled voltages to show the voltage output when the coil is in different positions. One line has been drawn for you. So when the coil was like this with AB on the left, the question says that it gives us positive 6 volts. Similarly, when the coil is rotated through to a position when AB is here, because now it's cutting the field lines in the opposite direction, the EMF induced would also be opposite, right? So then it's going to be -6. So let's look at our options here. So with AB on the right, I'm going to get 6 again, but this time it's going to be negative. With the coils vertical, when the coil is vertical with AB on the top or AB on the bottom, there are no field lines going to be cut in that position. And in that case, there would be no EMF induced. So both of these will not induce any EMF. Yeah, this is the good question that we were talking about. Both an AC generator and a DC motor contain a coil and brushes. Figure 9.1 shows how the brushes are connected to the coil in an AC generator. Draw a diagram to show how the brushes are connected to the coil in a DC motor. So in the case of the AC generator, see that you have two of these, two of the rings, right? The slip rings, you have two of those. But in this one where you have the split ring, remember that it's going to be like this. So they are going to be separated through this. And from here, you'll have the coil connected. And these will be connected to the carbon brushes. Right? And then the carbon brushes are connected to the rest of the circuit. All right. So making this, it's important to see that there is not a complete coil here. This is that one ring, and there are these halves in the middle. And at each time, there is only one carbon brush in contact with any half. It's not in contact with both of these at once. State why there are forces on the sides of the coil in a DC motor. So the idea is that a force acts on a current carrying conductor. That's what CCC stands for in a magnetic field. All right, 10. Carbon-14 is an isotope of carbon. It undergoes radioactive decay with a half-life of 6,000 years. Age of a sample of wood is found using the carbon-14 that it contains. You know, this is how we do carbon dating. Describe what happens during radioactive decay. So we know that there are emissions from the nucleus because of these changes in the nucleus. Which could be either of alpha, beta, or gamma. All right. Part B, count rate of the carbon-14 is initially 16,000 counts per minute. On 10.1, draw a graph to show how the count rate will vary over the next 24,000 years. As we were told above, the half-life is 6,000 years. Just as how the number of radioactive nuclei or the radioactive atoms will decrease, exactly the same way the count rate is also going to change. So if it's initially 1600, then after one half-life, which is 6,000, it's going to get halved. So then it's going to be this much. Then after another 6,000 years, another half-life, it's going to halve further. So half of 800 is 400. Then after another half-life, which is going to make it 18,000 years, it's going to halve further. And I think that's actually we can show the last one. So that's going to be half of 200, which is 100. And then you just join all of these with a curve as best as you can. All right. C, name the apparatus used to measure the radiation from the sample of wood and describe how it is used to measure the count rate. So the apparatus used is a GM tube and a counter, or you can also say a rate meter. Both of these are correct. So how is this used? So you just know that you connect the tube to the rate meter. And for the corrected measurement of the count rate, you subtract the background radiation. Part D, describe how the count rate from a sample of wood is used to find its age. So how do we use carbon dating to find the age? So how you do this is that you measure the count rate from fresh wood, and then you compare with the wood that you are trying to determine the age of. So compare with wood we are trying to find the age of. And then you can say we determine the number of half-lives elapsed. Right. So for example, if there is a difference in the count rates, so you can see that how many half-lives would have elapsed. And then you multiply by this to find out the age. The answer isn't showing up on screen. It is showing for the rest of us, I guess. Leave and join again. All right, last question is space physics. 11.1 shows details about 8 planets in the solar system, average distance from the sun, the orbital period, and their average surface temperature. So you have the planets, distances from the sun, orbital periods, average surface temperature. Complete 11.1 by adding the names of the 3 planets that are not given, right? So you know the mnemonic. My very easy method just speeds up naming. So the first M is going to be Mercury. This is the closest one. J is just Jupiter. S is Saturn. And U is Uranus. And N is Neptune. Calculate the orbital speed of Mars as it travels around the sun. So orbital speed, the formula is 2 pi r over t. Again, look at the units. They do want the answer in kilometers, so do not convert this. So we're doing this for Mars. For Mars, the distance is this. 2.3 into 10 to the 8. And time is also given in seconds, and that's also what the answer is wanted in. So 5.9 into 10 to the 7. Oh, I just forgot the 2 pi, right? So when you find this out, this turns out to be 24 kilometers per second, correct to 2s. Part C, describe the relationship between the distance of a planet from the sun and its orbital period. So with the distance and the orbital period, we can see that as distance increases, orbital period is also increasing. Right now, we don't have to write down the relationship. So you can just say that as distance increases, orbital period also increases. I'm saying that right now we did not have to explain why this is so, but it could be asked. So remember that the reason the orbital period increases is because at a greater distance away from the sun, the force that the sun applies also decreases. So each of the planets moves slower and hence they take up more time, right? That's why the orbital period increases. Describe the relationship between the distance from the sun and the average surface temperature of a planet. In your description, include any anomalies. So what are anomalies is what do not obey the trend. So if I look here, distance is increasing. So temperature increases, decreases, 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 and decreases. So it does decrease throughout. And also you should know the reason for this is that at a greater distance, less radiation from the sun reaches those planets. So the only outlier is this guy here, Venus, right? So you just need to include this. Otherwise, you don't need to really explain why this does not obey the trend. So as distance from sun increases, we would say the average surface temperature decreases except for Venus. All right, so that's this entire paper that we did. So now the summer 23 paper 22 is your homework. All right. For that, you'll have the recording, and then in the next one, we'll do winter 23 paper 21. All right. So that's it for this session, guys. Hope you guys learned something. And as always, if you have questions, you can ask on the platform. And do complete your homework because that's how you will build up that pace. All right. So see you next time then. Allah Hafiz.